Okay, section 3.8 is we're going to be taking the derivative of logarithmic and exponential functions. Mm-hmm. Uh-oh. Okay, well, we'll find those for you. Probably. All right. So, the major theme of this chapter is that we're going to talk about how to find the derivatives of different things. We kind of stopped for a minute, and we did the implicit differentiation. And then we talked about as rates of change and stuff. Remember, the reason that we're doing this together is that exponential functions and logarithmic functions are inverses of each other, right? Right? So if I say, this is just review real quickly here, just remind you, if I have e to the ln of x, what does that do? These are inverse operations, so I just get back to e and ln cancel each other out, right? Now just get the argument, which is x. Or, if I have the ln of e to the x, what's that? X. That's what tells me that these are inverse functions. Okay, is that when I do the operation, I'm left with the argument. Okay? The other thing I want you to remember is that the way we worked with the ln of x, remember, is that we changed it into an exponential equation. Right? Most of the time. And what's the base of an ln? E. So I'll have e to the answer of an ln question, because the answer to an ln question is the exponent, right? So e to the y is equal to the argument. These two things are equivalent. Okay? Just reminding you of this stuff. What? That's the definition. You need to have that memorized. If you do not have that memorized, you need to get it memorized. Okay? Okay. Now, there's one last rule that I want to remind you about that we didn't use a whole lot before, but we are going to use it here in calculus. If we have b to the x, where b is some number besides e, okay, it's just a number raised to an exponent, then I can rewrite that, because by the inverse operation, I know that e to the ln of b to the x just all reduces out to b to the x, right? Yep. Cancel each other out. And by the properties of logs, I know that if I have an exponent on the argument, I can bring it down in front, right? So e to the x times the ln of b. So you can always take any number raised to a power and you can turn it into e raised to a power. And the reason that we do that is because we have a rule to take the derivative of e to the x, or e to an argument, right? An exponent. Yes? So what this does is it allows us to use that same rule for anything raised to a power that's a variable. That's all that was. Just a quick reminder, just a review of that stuff from Algebra 2 that we're going to be using. Okay? Now, the calculus part of this is we've got theorem 3.17, which is just the derivative of the ln of x. So the derivative of the ln of x with respect to x, what? Thank you. Derivative of the ln of x. Okay, so if I'm taking the derivative of the ln of x, what I get is 1 over x. As long as x is greater than 0. Now, why did I have to put that x had to be greater than 0? Can't have 0 in the denominator, so that's why it can't be equal to x. But why does it have to be greater than x? Does anybody remember? The ln is not defined for negative values. Okay? And since it's not defined for negative values, then we a lot of times will talk about the ln of the absolute value of x, because there's sometimes when I need to know what's going on. The ln is not defined for negative arguments. I can't take the ln of -3. If you type that in your calculator, it's not defined. It'll give you an error message. So there's my theorem. Now let's talk about how to use that. So if I have y is equal to the ln of 4x. This is a chain rule. I want you to notice it's a chain rule because I got more than just an x in as the argument, right? Okay. So I'm going to take the derivative of the ln part, which is 1 over the argument. Just like it appears. Thank you. Yep, derivative of y right now. It's the derivative of the ln of an argument is 1 over the argument times the derivative of the argument itself if it's more than x. So you get 4 over 4x, but that just reduces to 1 over x. Okay. Yep. Well, if it's just a number times the x. Now, this 4 is the derivative of the guts. I did the chain rule, and that's 4 over 1, so the 4 goes on the top. I took 1 over the argument, just like it appears, always. And then you have to take the derivative of the argument, whatever it is, every single time. Okay? Okay? On the second one here, that's in this example, does anybody want to tell me what I have to watch out for? It is the product rule. That's exactly right, because I've got this x times this ln of x. So the derivative of y is going to be the first times the derivative of the second. 1 over x times the derivative of x is just 1, so I don't need it, right? Plus the derivative of the first one, which is 1, times the ln of x. So x times 1 over x is just 1, plus, and 1 times the ln of x is just the ln of x. So the derivative is 1 plus the ln of x. That was A, part A. This is part B. Here's part C. Y is equal to the ln of the absolute value of the secant of x. They'll do this a lot of times because they don't want you dealing with the whole fact that sometimes the secant is a negative number. That way you can go ahead and take the derivative of this thing. So I put it in the absolute value bars is because the secant of x is sometimes a negative number. Okay, we'll do that in just a second. Remember that I got to do the chain rule when I take this derivative. So the first thing I get is 1 over the secant of x, right? because it's always just 1 over the argument. Then times, now I need the derivative of that secant, which is secant times the tangent. Okay, so if I simplify this, I get the secant of x times the tangent of x over the secant of x, right? Because when I do the derivative part over there, that is over 1, so it goes in the numerator, yes? And then everything's multiplied together, so the secant of x reduces out to 1. So the derivative of the ln of the secant of x is just the tangent of x. Always, every single time. You do 1 over whatever the argument is, and then take the derivative of the argument. And if you'll do that every single time, that is the derivative of the ln. Okay? Because that's the formula. My formula that I start out with here is the derivative of the ln of an argument is always 1 over the argument every single time. You just got to memorize that. Okay? Good. But you got it now, right? All right. So, last one. We've got, lost my page, y is equal to the ln of x squared over x squared. I don't need absolute values because x squared is always going to give me a positive number, right? Okay. What's going on here, though, that I got to pay attention to? I got to use the quotient rule, right? Okay. So the first derivative is low times the derivative of the top. The derivative of the top is 1 over the argument, just like it appears, times the derivative of the argument, 2x. Minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. Okay. Now, we need to simplify it. So x squared and 1 over x squared just multiplies together to give me 1. So that just gives me 2x minus 2x times the ln of x squared. It's okay if I put the 2x in front. Over x to the 4th. I do want you to notice that I do have a common factor there in the top, so I can factor out that 2x. Yeah, just in the top. Factor out the 2x out of the top, and that leaves me 1 minus the ln of x squared over x to the 4th. And now, like you say, the x reduces out. This 1x in the top reduces with that 4x's and leaves x to the 3rd in the denominator. So, the final version of my derivative is 2 times 1 minus the ln of x squared over x to the 3rd. Because that's the argument of an ln, and I can't take an x out of that. Okay. Any questions about that? So like I say, that idea that we had a while ago that anything raised to a power can be written in terms of e raised to a power gives us the next theorem. I'm not going to go through the proof for it, but Theorem 318 tells me that as long as b is greater than 0, then for all x's, if you're taking the derivative of a number, a positive number, raised to a variable, then the derivative of that, the pattern for that, okay, Megan, is the number itself, just written down again just like it is, times the ln of the number being raised to the variable. Okay, that's just the pattern. If it's a number raised to a power, then the derivative is the number raised to the power still, but it's multiplied by the ln of the number. So example 2, if we have that f of x is 3 raised to the x. This follows my pattern, right? It's just a number raised to the variable. Yes? So the first derivative, I just write it down again just like it is. So I've got 3 to the x, but then I multiply it by the ln of 3, the number. That's it. That's how you do it. Yep, just plug stuff in to get that one. Now on the next one, you have a little bit more, but it works pretty much the same way. So they tell me that g of t is equal to 108 times 2 raised to the t over 12. It's multiplied by a number, but what do I know about all of my derivatives that I had so far that had a coefficient? You just bring it down, right? Just bring the coefficient down. So when I take the derivative of g, then I'm just going to bring down the 108 just like I've been doing because it's just a coefficient and it's going to work that way every time. Then to the t over 12, but I do have a problem now because I also need to do the chain rule here, right? Yep. So I need the derivative of t over 12, which would be 1 over 12, right? Because that's just like 1 over 12 times t. So it'd just be the coefficient times the ln of the 2. No, not because the variable's in the exponent. Anytime the variable's in the exponent, I can't use the power rule like we've done before. And now I need to simplify this. Yeah, so 108 times 12 would be 9. And then you can move the ln of 2 up in the front if you want it, or you can leave it back behind. Well, you can stick it in the calculator if you want to. You could have one of those if you wanted it. But you're the one that said if I had one of those. All right. Okay. Okay. So you had a question? Oh. Well, actually, I just took Blake's word for it. You question Lake? All right. Okie dokie. So anyway, here's just another example. This is the quick check in your book. And it is quick check number 3. We didn't do 1 and 2. I didn't see them. Okay, it says suppose A is equal to 500 times 1.045 raised to the t power. It wants us to find the derivative of A with respect to t. Okay, so what are we going to do? Got to bring the 500 down because it's just a coefficient. And I don't have to worry about the derivative of the exponent this time because the exponent is just t, and the derivative of that's 1. Okay? Any questions? Yes, that's it. Right. Okay, so let's just look at some more of these. Because I want to show you, I want to remind you about the difference, because somebody said a while ago, do I just use the power rule? So I'm going to kind of mix you up a few, where sometimes we use the power rule and sometimes we use this new exponent rule. Okay, thank you. It's going to be that way on the test, right? Okay, so this is y is equal to x to pi. Is pi a variable or is pi a number? Pi is a number. So in this case, I have the variable raised to a number. So which rule am I going to use? The power rule. So the derivative of this is going to be, I'm going to bring down the exponent, which is pi. I'm going to have the argument, which is x, to the pi minus 1 power. Okay? And I don't have to take, it's not a chain rule because the argument's not any, I mean, the thing's being raised to the power is not anything but x, right? The derivative of that's just a 1, so I don't have to worry about it. My pie is ugly to you. Oh, whatever. Okay, so are we good? All right, let's look at B. What if I had written it this way, though? Now we have to use the exponential rule because this is a number raised to a variable. So the first derivative of this is what? Pi to the x, right? And then I have to take the ln of pi. Take the ln of the number part. Good? That's all there is to it. Let me give you another one. It's an interesting one. Y is equal to x squared plus 4 raised to the e power. Yeah, this is C in the same example. Now, this is what? Chain rule, right? That is the chain rule going. But just simply because the thing being raised to the number power is more than just x, right? So I'm not going to use the power rule, though. Everybody see that? I'm not using the power rule. Why? No. E is a number, so what am I going to be doing? The power rule. Good. I know. I was seeing if y'all were listening. I'm sorry. All right. I was seeing if y'all were paying attention. So we're going to bring the E down. Wait. Whatever E minus 1 is, don't forget to write that down since we're leaving it. Excellent job. So we are using the power rule because the variable's in the argument and the exponent is a number. Ln of a number is a number. Ln of x is not a number. Yep, E is an. Those are my two irrational numbers that we have found through experimentation that we know exist out there, besides the irrational numbers that are the square roots of non-perfect squares. Right. Yes, there's not going to be, there's no ln in my derivative because this is not a variable, it's a number. You got to be paying attention. E and pi are not variables, they're numbers. Okay? Remember that when you're doing tests and homework and all that other stuff. Okay? Alrighty then. So, example 5, that we want to be able to actually be able to find horizontal tangent lines. Now, we've talked about finding equations of lines a whole lot, but why do we ever find the horizontal tangent lines? Because I tell you too, that's a good reason. But what is going on when a line is the tangent line is horizontal? It's touching at a turning point, right? It's a place where it's been going up and it's turned around and going down, and that's when my slope is exactly 0, right? And so a horizontal tangent line is one that's got m equals 0. Okay, so that's the connection with what we've been doing. And we have done this before, but I just want to always remind you because y'all forget from one day to the next. Okay, so what we're doing in example 5 is we're going to decide, does the equation f of x equal x raised to the x, as long as x is greater than 0, have, or does it, would that be have or has? Does this equation have, there we go, any horizontal tangent lines? So on a test, that's a possibility of a question. It's going to give you a function and ask you to determine whether or not this thing has any horizontal tangent lines. So, how do you decide that? You want to know, is the first derivative ever equal to 0? What's greater than 0? No. This gives me the right. Yes. Okay. And since I have the right. Okay, so this doesn't work for us. We don't have anything where it's a variable raised to a variable. Right? So I'm going to rewrite that as e to the x times the ln of x, using that rule that we had before. Okay? Do you want me to go through the process of how that came from? Okay. X to the x can be rewritten as e to the ln of x to the x, right? And then I can bring that x down in front, so it becomes e to the x times the ln of x. Yes, because e is just a number. All right? Well, the reason it is because we just got through saying that x is a number greater than 0, so I can use it. Yeah. Yeah. Remember, if I have the ln of an argument that's being raised to a power, then one of my properties that I have says I can bring the exponent down as a multiplying front. Okay? Are we good? So now I have this in a form where I can actually take a derivative. So I'm going to use, what was it, Theorem 17? That was the exponential rule, okay, which said anytime I take the derivative, it's either 18 or 17. Okay, so it's e to the same argument, right, times the derivative of the argument. It's really actually 18, I think, wasn't it? The first times the derivative of the second plus, remember when I have it, that's this argument, this exponent right here is actually a product, right? So I've got to use the product rule when I take its derivative. Simple 5. Times the ln of x. Right, we did this, wasn't that like example B on the example 1 or number? It's like one of the first ones we've already done. Yeah. Okay? But you remember this is my rule, right? I write the thing, I've got e to any exponent. I write e to that same exponent, but then I have to take the derivative of the exponent. That's all I'm doing. I think that's the 8. Is it 3.17? Okay. That's right. Anytime this exponent is more than x, you got to take the derivative. I missed it. Oh, because that's the power rule. We already knew that, right? Okay. Now we need to simplify this. This is e to the x times the ln of x. And so this one's 1 plus the ln of x. And you're done with that. Okay? Almost. We're done with the derivative part, right? Yes. More than x for the exponent. Then the derivative of that's 1, so it didn't matter. You can find the derivative of it, but it doesn't change your... Yes, if this was a variable raised to a number, then you use a power rule. Huh? All right. Now, remember what we started with this problem, because we had already found this derivative. This shouldn't have been a new idea. Okay? But what were we trying to do? We were trying to decide if this function has any horizontal tangent lines. So what I do now, once I find the derivative, to figure out if it's got any horizontal tangent lines, I've got to set it equal to 0. I take the derivative and set it equal to 0, and that's going to tell me, do I have any equations? If I can get an x value, that means that x value, there's a horizontal tangent line right there on that curve. Okay? So, I got to solve this. How do I go about solving this? No. This is multiplied by this. No, I don't want to distribute. It's in factored form right now. When I have something in factored form, how can I solve it? I can take each factor and set it equal to 0, because it says this can be 0 or this can be 0, right? So I've already got it in factored form. Now I just need to take each factor and set it equal to 0. Anytime you have an equation in factored form, you can and it's set equal to 0, you can always take either factor separately. You want to do this one first? Okay, so what am I going to do? Subtract 1, so I get the ln of x is equal to -1. Are you sure? Remember how to solve this? That's right. You have to exponentiate both sides. So in other words, I'm going to take each side and make it e raised to that piece. So e to the ln of x would just be x, and e to the -1 is just 1 over e, right? Mhm. Okay. So that piece works, and that's going to give me, it is a positive number. You're exactly right. Okay, so that gives me the point 0.368. Is that good enough? All right. But if I'm looking for the point where this has a horizontal, what do I need to do with that value now? And to the original equation to find the y to go with it. The original equation. Yep. So e to the e. Or 1 over e to the 1 over e. Right. My original equation was y is equal to x to the x. So if x is 1 over e, then I got 1 over e to the 1 over e power. Right? Since he has a calculator in his hand. Works for me. So 0.7. Mine says 0.692. Okay. So there's a point where I do have a horizontal vertex. Now let's come back over here to the one Emily wanted to skip. Okay. So no, they cannot. Because you have the x in front of it. Now you can put the x back. Then you can cancel it out. So you get x to the x is equal to 0. Okay? Now, what power can you raise? I mean, what 0 to the 0 power, remember, is anything to the 0 power is 1. Anything to the 0 power is 1. Otherwise, my rule doesn't work. And so is there any way that I can get a 0 out of this? No. So this gives me a no solution piece. Okay? Good. All right. There it goes. That's all right. Next theorem. We're going to be talking about the derivative of general logs, not just LNs, but all logs. Yeah, it had the 1. Just didn't have more than 1. Okay? So, theorem 3.20. Okay. And general log looks like this. Remember, log base b of x. Remember, it's got some other base besides e. That's a general log. So not an ln. But since they work the same, right? Have you remembered that all logs kind of work the same as ln's before with our other properties? Then it's probably true that these are going to work very close to the same. The derivative of the log base b of x is equal to 1 over x times the ln of b. This time the ln of the number is just the ln of the base, right? That's why it's a little different, and it goes in the denominator of the fraction. And the same thing, if you have a situation where sometimes you get a positive value and sometimes you get a negative value, and they qualify that with putting the absolute value around it so that you can go ahead and find the derivative, you still get this. What now? So it's 1 over the argument times the ln of the base. Okay? All right. So example 6, part A. So the first derivative of this, yes, log base 5 of 2x plus 1. Oh, yes, you're right. We will have to do the chain rule because this is more than just an x. Good, good. That's a way to see it. All right, so in my problem here, I do 1 over the argument just like it is. Right? Times the ln of the base. But since my argument is more than just x, I do have to then multiply that whole thing by the derivative of the argument, which is 2. Right. Chain. Well, they go through and go ahead and pull the 2 and the ln of 5 in front for some strange reason. Because this is just a number part right here, so they pull it out in front like a coefficient. But they haven't really done anything else to it. That's it. We good? What's wrong? Except what? What's wrong? No, you don't do more to it. You just do the rule and simplify it if you can. They just, for some reason in the answer key, they pulled this out in front. Because, see, this is a number and this is a number, so they just pull it out in front so it looks like a coefficient. Not sure exactly why they bothered to do that. I'm hoping that would not, if it was a multiple choice test, that you would know that this is the same as this. Okay, that's the only thing. All right. Okay, so come on, change. The last objective here in this, or the last little category they have in this section, is called logarithmic differentiation, which we've already been doing some of this. Yeah. Now, the reason that we talk about this here is that they give us an equation. They say, look, check this out. What if f of x is equal to x to the third minus 1 raised to the fourth times the square root of 3x minus 1 over x squared plus 4? If we just started taking the derivative of this, we can do that, right? But that's like the chain rule with the quotient rule with the product rule. That would not be fun. It would be very tedious. Now, we could probably do it, but it would be ugly. A little slow going. That's exactly right. Yeah. But remember that we have all those LN rules that allow me to take an argument that's like multiplied and divided like this and pull it all apart and make it into something a lot easier. Remember that. Just give you a quick reminder. The ln of x times y over z becomes the ln of x plus the ln of y minus the ln of z. You remember that product? That was last year. And the year before that in Algebra 2 we talked about it. So I just want to remind you of that old property. And so if then I took the ln of both sides of this equation, right? Wouldn't it make it a whole lot easier if I could use that property and pull it apart and just find one piece at a time? So and I have the right to do that, right? The ln of the f of x is equal to the ln of x to the third minus 1 to the fourth times the square root of 3x minus 1 over x squared plus 4. Now I'm going to use the rule, the properties of LNs, and I'm going to rewrite that. That's the ln of f of x, and that's equal to the ln of x to the third minus 1 raised to the fourth plus the ln. Now, I'm not going to write that as a square root. I'm going to go ahead and write it as 3x minus 1 to the 1/2. Good. Minus, remember I subtract off anything that's in the denominator, minus the ln of x squared plus 4. And now remember, I don't have to have those exponents on those arguments, right? I can actually use the power property. And I have the ln of f of x is equal to 4 times the ln of x to the third minus 1 plus 1/2 times the ln of 3x minus 1 minus the ln of x squared plus 4. Now I have this, and it's in a much nicer form because now I can just take the ln of the derivative of each one of those ln's separately because they're all added and subtracted. Good. All right. So now when I take the ln of the f of x, then that gives me the derivative of f of x with respect to f of x. Okay? The derivative of f of x with respect to f of x. I took the derivative of it. Took the derivative of it. Okay? So it's what? Squared. 3x squared. Times 3. Excellent job. Okay? Yay, Emily. Now, of course, we are going to want to simplify that a little bit. Okay. We're going to have to. Okay, so if I simplify this, and I solve it for f, the derivative, right? I get f of x times so I've got the 4 times the 3x squared, and that goes in the numerator. Solved it for f of f, the derivative. So, am I putting f by 4 in there? Okay, so 4. Wait. What's wrong, Jake? I don't get how the f of x from there all across the equal sign. because I multiplied both sides by f of x to get rid of the denominator that was here. Okay, I multiplied this side by f of x so that that would reduce out, and then I multiplied this side by f of x. Okay, we're good. All right, good deal. So I've got the 4 and the 3x squared that are both whole numbers, so they go in the numerator. So I've got 12x squared over x to the third minus 1 plus, how about 3 over 6x minus 2 minus 2x over x squared plus 4 is exactly right. Okay, now, not exactly through, because I don't want to leave it at f of x, but what do I know f of x is equal to? That's exactly right. X cubed minus 1 raised to the 4th times the square root of 3x minus 1. Okay. And then I can just write all this stuff down. Okay? And that's quite enough simplification. Yeah, I'm doubting we'd be able to do anything with that. Okay? Don't want to do all that. Okay? So, now that you have the rule for finding the derivative of the ln, then a lot of those things that we've been fighting with doing the product rule or the quotient rule, we could now take the ln of both sides and actually do it this way. The only thing that you're going to have to remember is that when you take the derivative of the ln of f of x, you get the derivative of f of x divided by f of x, right? I mean, I kind of skipped that step and I just wrote it down, but you understand why, yes? Because the derivative of the ln of something is 1 over that thing, right, times the derivative of that thing. So I went ahead and put it together, kind of slid past it, and it messed Jade up a little bit, I think. Okay? So any questions about how we got that answer and how we could use it in the future? Instead of taking things that are nasty quotient rules and doing the quotient rule with it, I can take the ln of both sides. I can pull this nasty quotient apart so I don't ever have to do a quotient rule. Okay? Yeah, probably so. Okay, so your homework on this is on page 199, and I want you to do 9 through 78 multiples of 3.